Otherwise, I guess we'll start the discussion, eh? Okay, cool. So I guess I'll start talking here like I did last time, but hopefully everybody should be perfectly comfortable jumping into this discussion here, because this is a discussion group, not a lecture group. So let me just pop up my solutions to the exercises here just as a place to start talking. Okay, I am sharing, and here we go. Okay, so
I haven't been hearing any sound coming from you guys. Is that? I think.
Yeah, we've lost. I think Paul was talking, and then.
Oh boy.
Yeah, something happened.
Okay.
But we still see his video. He's
right, there we are.
And we can see ourselves, so that's great. That's cool. Not too much. Yeah, it's actually pretty fluid in a way.
Can you hear me now? Any luck?
Yes.
Yeah.
Okay, so you couldn't hear me when I was talking just then?
No.
Okay. Okay, I'm going to start the screen share and see what happens. Okay, how about now? And I'm starting the screen share, and okay, what do you think? How's this?
Yeah, I can hear you.
And
can't hear you anymore.
Yeah, I can see your screen, but I can't hear you. That's kind of weird.
Okay, this is suboptimal setup here. Okay, hold on a second. So apparently when the webcam shuts off because I switch over to screen share, it also shuts off the audio.
Maybe you'll just need to turn back on the dual monitors, because that's what you had last time.
Okay, let me try switching this here. Hold on one second here. Okay, a technical issue that I did not anticipate. Okay, let me think about this for just a second here. Okay, well, I think about this. Does somebody else want to give their impressions of section 1.2 if you've had a chance to look at it at all?
Well, can I just say something quickly? I would like to say that the first thing that is surprising to me is the way Scheme handles recursion, which is not recursion, but like iteration rather. Like if you come from a language like C or Python, you can have for loops or while loops, and with Scheme it's like a call to the same function, right? Which is not a recursion. So that was the first thing that was noteworthy.
Yeah, so there's a distinction between sort of the recursive structure of a function and then the actual recursive shape of the process that's generated. So I think that's sort of one of the key points they were trying to make. So something can look like it would be recursive in another language, but when it's actually executed, it ends up creating what they call an iterative process.
Right.
And so if you've heard of tail call optimization, that's what's going on here. So basically, what happens is it lets the interpreter throw away the current stack frame if it can be determined that it's never going to be needed again. So if you watch the lectures, the ones that Sussman and Abelson gave to Hewlett Packard, you've got the example of, you want to calculate something, but you're lazy. So you write down, basically what you need to solve the next step of the problem, and you hand it to the next person. And if you never have to see that again to complete the calculation, then you're done. So basically, you're out of the picture. But let's say that you've got a pending add request. So you say, okay, I need to add two numbers together. So I know one of the numbers. I need this other number. Okay, so you ask the next person down the line to calculate the next number in the chain for you. And if you have to have a chain of people solving these problems, you end up with a recursive process because you get a bunch of people who are effectively standing around waiting for responses. But for the recursive process, you tell the next person both what your current state is and what needs to happen to calculate the next step. And then they have enough information to calculate everything for that themselves. So that's sort of...
do you mean the iterative process? That's what's...
The iterative process, yeah.
Right.
And so there's a lot of friendly structures which are introduced, and some of the ones even in Scheme or Lisp look like more traditional iterative loop type structures, and certainly Lisp has straight iteration. But Abelson and Sussman are making a point here that you don't actually need these to produce your programs. So they're being very selective in what they introduce over these first three sections of the book here, the first chapter. And they make the point that they don't actually introduce assignment till something like chapter 3, which is a little surprising. So
define is not considered an assignment?
Define is considered naming. And they make that distinction actually in the teaching notes very carefully.
Mm.
So basically, all define does is define gives a name to something. And they make a comment in one of the footnotes that you have to put your defines if you're doing a block-structured program. There was an example of that at the end of section 1.1. That's basically where you've got procedures nested inside of other procedures.
Right.
And you can't see the names from outside. They say you have to put them all at the front, and you can't rely on the order of definition for those.
Wow.
So,
yeah, I was actually surprised by that aspect of at least the schemes that we're using, and even Clojure, that there's no forward naming. I don't know what that's called, but I know that's that's called something when you can use functions that you have not yet defined, but will be defined in the scope that you're using the function in. So in JavaScript, for instance, you can do this, but in Clojure and in MIT Scheme, you cannot do this.
Yes, because you're doing it. The question basically is that is it runtime resolution of these, or is there a compile time step where if the names are actually bound? And since Clojure is running on top of the JVM, that places some fairly strict limitations on the types of fluency that can be allowed in those types of specifications.
Right.
Is that hoisting in JavaScript?
Excuse me?
Is that hoisting in JavaScript?
Yeah, that's called hoisting. I forgot the name. That's exactly what that's called. Yeah. So hoisting is allowed there, but it's not allowed in. I don't know what other language you can hoist in. I wonder whether I think you might be able to do it in Ruby, but I'm not sure.
In languages where it isn't allowed, there's usually a facility that allows for a declaration as opposed to a definition. So basically, you just stick a placeholder in the environment saying this is a legal name, which you're going to have to resolve at some point in the future.
Yeah, well, in JavaScript, you don't. That's the thing. You don't actually do that. It's just. But you're right. Clojure does have a way of predefining names of functions that you're going to use. But I don't really consider that hoisting. I just consider that what you do in C++, where you just name the functions that you're going to use.
Mm-hmm. I'm still trying to sort out why my other microphone isn't working here. Otherwise, somebody else might have to do the screen share portion of this here. I can't get it shared successfully on mine. Huh. Go ahead.
But you have your notes are in org mode, right? So
My notes are in org mode, but they're also compiled into a PDF.
oh, okay.
So the PDF, I sent the link. So if you look at my GitHub, which is Path of Programming, and then there's the the repo name is SICP-exercises. If you just go to the raw mode, that will pull up the PDF.
You just do it in GitHub. It's pretty. It's easy to read along. Just what how it's rendered.
Yes, actually, I was amazed at what a good job it did at rendering the just the raw org mode stuff. It did everything but the LaTeX.
Oh, yeah, that's pretty cool. Wow.
I am. Everybody's muted except me. I don't know why that is. Okay, well, I guess I'll just keep talking for a little bit here. I'm just looking at some of the controls here that I have available. Oh, I can eject people. Exciting. But I'm not going to eject you, don't worry. Okay. Anthony's joined. Hello, Anthony.
Hey.
She was born in 1908. She washed lice from her hair with kerosene. She was out with...
Okay. Okay, yes. So somebody has, Rowan has posted the link to the org mode, and if you go to the PDF one, if you'd rather look at it that way, that's cool. So I guess maybe that's the way we'll follow along. So just go to the GitHub webpage there, and we'll look through it that way. So that's a little disappointing because it's always more fun to do it in Emacs. So does it automatically mute people when I talk? Is anybody else trying to talk, or are you just listening to me natter on?
I'm just turning my microphone off because my kid is making a lot of noise. So I'm trying.
Okay, no, that's cool. Okay, so yeah, so there's this issue of recursion and iteration. And actually, Steve at the KOP session made a great point that section 1.2 is about consequences. So, you know, section 1.1 is really mostly about familiarizing yourself with the syntax of scheme. You know, it's basically figuring out, yes, we got parentheses, yes, you know, we got these special forms where sometimes we evaluate things, sometimes we don't. But there are those, you know, important exercises that are, you know, pretty silly and mechanical in one sense, where you do the substitution, and which just gives you a way of thinking about, you know, what the shape of the process that's created is. And then that leads directly into what's going on in, like, exercises 1.9 and 110. So exercise 1.9, I guess people are going to have to flip over to that in the org mode or in the org file on GitHub. So the first example is this just a simple example of adding two positive integers using these two different methods. And you know, that sort of gets right down to what that is. What are the pending operations? So if you look at the shapes of these two procedures in the problem definition, the first one has the increment on the outside, and the other one has the addition on the outside. So you know, you've got two different shapes of procedures that are going to result from this very different change. And flipping down to how it results, you start looking at, the procedures. And actually, one of the points that Abelson and Sussman make in the teaching notes is that this is useful because it reminds you that it is possible to just, that things like addition can be just another procedure. They don't necessarily have to be built into the language. And in Scheme, it depends on the scheme whether it's going to toss an error or not. But in Scheme, you can just, if you feel like it, redefine the plus operation, which is what we have going on here. So we're implementing plus in terms of these simpler operations, just incrementing and decrementing. And so this is a pattern which is going to be followed throughout the book, where you sort of start looking at all the things you take for granted in the language, and you build them up from other pieces. And as you move along, you start assuming that more of these things that are going on under the surface you can just take for granted. And it can be useful to think about them in particular ways. So, for example, they make the point about the substitution method for figuring out what a procedure does. This isn't necessarily the way the computer is actually executing it. So if you look at the the difference between normal order and applicative evaluation, it's not the case that the computer is actually doing textual substitution in all of these cases, but saying that, okay, well, we can behave as if the computer is operating in this way, and it will give us useful insights into the process. So in my opinion, 1.2 is really about beginning to build up a mental model of the way that the computer is working, the way that the languages work, the way when you write something, you start to build the linkage between, first of all, the syntax, the text that you put on the page, then you've got the, sort of the hidden stuff under the surface, which is the shape of the process that's generated. And then there's the final step, which is the result, which is what you actually see at the end. And procedures with different shapes internally, with different processes, can still have the same result. And that's what a lot of these exercises, where you're flipping back and forth between, okay, well, here's a recursive procedure, turn it into an iterative procedure. And I know at least one...
Paul, I have a quick question about that. I was wondering, when I came across these exercises, I thought, oh, wow, this is a pretty interesting technique to use to kind of visualize processes. But then I was wondering, do you know if there is a way to actually do this automatically, not by hand, where I could just sort of see the substituted patterns instead of doing it by hand?
One way of doing that is using macros, because macros are all about text substitution, exactly. And if you, macros haven't been introduced in the book yet, and actually I was meaning to look at if there was a tidy way to do this for my write-ups, but I just didn't have time. But there's usually a macro expand functionality. So in Clojure, you've got macro expand and macro expand 1. And these are both excellent tools for sort of looking at what happens when a macro executes. So macro expand 1 does one step of substitution. And so if instead of functions, which Abelson and Sussman call procedures, if we had macros, then one pass of macro expand 1 would do exactly the substitutions that we're doing manually through a lot of these exercises. So exercise 1.9, that's exactly what's going on.
All right, thanks.
Yeah, I'm not sure if macros are covered in the book. That's an interesting question, because of course they're key in a lot of ways to lists in general. And this isn't really addressed at this point, but this is sort of one of these interesting things that sort of falls out of the syntax, which is discussed in section 1.1. So in 1.1, we've got these examples of special forms. And so there's these questions, why are special forms important? What happens if we actually evaluate both channels of a list, of an if statement or a conditional? But the key with macros then is it lets us reuse all of these special forms. So, for example, usually in a language like this, you'll only have cond, C-O-N-D, or if implemented, and then one will be implemented in terms of the other as a macro at the higher level. From the user's perspective, you don't see the difference, but that's the result in terms of the code you actually execute. So again, I mean, if you haven't tackled the list stuff before, there's a reason they haven't really addressed it at this point, and I'm looking at the index here, and they have a single mention of macros on page 373. I'm just going to glance at that to see what they have to say about it. Okay, that's it looks like a really minor, okay, it's actually a footnote on that page. And they also mentioned the reader macro character. And that's also mentioned only in a footnote. So they don't consider that macros are really a significant part of what they're trying to teach with this presentation of scheme, which is actually, I think, somewhat interesting, because when you look at a lot of discussions of Lisp in general and scheme, you know, a lot of is made of its homoiconicity. That is to say that its structure is very well suited because of its regularity to manipulation of things by macros and other forms of code generation. So some of the code generation will be a bit more of an issue, particularly as we get into things like implementation issues. So one of the cool things about this book, I peeked ahead, even though I haven't worked through much more than like the beginning of chapter 3, but that was quite a while ago, the last time I attempted. But you're going to be actually writing a lot of these lower level features. So things like when we see the lexical scoping, when we see those procedures nested inside of other procedures, there are later exercises where we will actually be writing those facilities where we are looking up names in different scopes and actually implementing that from scratch. So something to look forward to, and that's one of the reasons to sort of stick with the exercises and try to grok as much of them as you can. So, I mean, any other thoughts or comments at this point? Okay, cool. Jump in should you have such comments. Okay, so I'm just flipping back here to the first exercise, exercise 1.9, just to look at it. I'm sorry that I can't share my screen without cutting off my audio. That's a really dubious feature of this webcam, I've got to say. So it's pretty straightforward. So so actually, just backing up just a second, how many people actually managed to do any of the exercises?
I did some of them.
Okay, Anthony, Christopher.
Yeah,
okay, so
I did some also. Okay, I was actually planning to work on them after hearing the, well, quote unquote, discussion.
Hey, no, that's cool.
I did one.
Which is what I did with the last one.
More, not much more than 1.9.
Yeah, some of them. I mean, they're definitely sort of a mixed bag in terms of how much effort they take to solve. 1.9, I think, is a useful one just for, sort of making that first tiny step towards this point they're making of the different shapes of the procedures. And so if you've gone through it, the first example there, you can see that you're building up all of these deferred procedure calls. So you've got these calls to inc that are building up because they can't be resolved until the argument actually has a value. And so you end up with a big chain, and the procedure starts belling out to the right there until you finally get the final result at the bottom of the recursion, at which point you can start rolling it up again. Now, the second one is this iterative procedure. And it, as you see, has a very different shape because you never have really any pending operations hanging around, because everything is more or less immediately substituted with the next step in the process. And so as you walk through that expansion, I think one of the significant things to look at there is the differences in the shape of that if. So if you look in the first example, that value of the if never changes from 5. So at every step, you're checking to see if your value is up to 5. In the second one, you've got this sort of shift where you've got the first line after the first substitution is if 4 and 0 are equal. Then the first option is 5. Then after you go through the first round of substitutions, you then are back to a new if that gets substituted in, but the values are different, so they've shifted. So you've got 3 and 6, and so sort of the logic is being rolled ahead into the next iterative state. So you don't have to remember, okay, well 5 is the original value of that second argument, because what you're doing is you're changing both arguments as they're passed along, as well as building up the final solution that's going to be passed back, which is that first option. And there are a bunch of exercises that the authors have you go through like this. So any questions on this? Because I think this is fairly significant, and I know at least one person posted something to the comments on this discussion session before the meeting. Okay. No, I guess we'll. Oh, do it. Was that a comment from someone, or was that just a microphone?
No. Can you hear me?
Now we can hear you, yes.
Yes. I was just going to say I thought it was a really a great exercise, just from the standpoint of like really explaining like what the initial chapter was talking about in terms of the shape that 2 different implementations could take on, even though it comes out with the same output. Mm-hmm. And just looking at like what it means by like constant space, and the fact that like one process or procedure could execute in constant space, whereas the other one, the interpreter, has to keep this chain of deferred statements in memory. So if you short circuit at any time, with the recursive iteration, like you couldn't get back to that original state. Whereas with it seems like the second one, if you put in like whatever the inputs were, or the arguments, at some point through the iteration, it would be able to execute the final output without losing the state.
So did you manage to do any of the other exercises along these lines? Any of the other converting recursive to iterative processes?
I made it through like 110 and then 111, getting through the tree stuff, but I hadn't been able to convert the other ones to like when we were talking about like to that point.
Okay, no, that's cool. The reason I was asking was because that was sort of the question that somebody asked. Was that Michael? I can't recall. This question of how do you, what's the thought process that goes into sort of flipping that switch yourself in terms of changing a recursive procedure into an iterative procedure? So looking at questions along those lines, so exercise 111 is one of those, if we want to flip ahead to that a little bit there. So, okay, so that sets up this, basically a recurrence relation, defining f of n equals n if n is less than 3, or f of n is equal to, a product of the three previous values if n is greater than or equal to 3. And so it has you produce both an iterative and a recursive procedure from this. And so, I mean, in my notes for the exercise solutions there, I have both of those there as frec and fiter. And I mean, there's a couple of interesting things here in the way these happen to be implemented the way I did them. So the first one is the specification of the recursion seems very natural, at least in this case, based on how the problem is specified. So more or less, all you're doing is what the authors call wishful thinking. I can't remember if they do this in the text or just in the teaching notes. But basically, you say, okay, well, if I need to solve a problem of this size, what's the other piece of information that if I had it, would it let me solve this easily? And that needs to be, in the case of this, a somewhat smaller piece. And we say, okay, well, in order to get f of n, we need those values for f of n minus 1, n minus 2, and n minus 3. And then simply by adding that if case there to catch the base cases that are specified, that is to say if f is less than n of 3, it's going to return n. It lets us come up with a very natural specification of the recursive process. And making the jump to turning it into an iterative process is kind of tricky if you haven't thought through it that way before. Did anybody else tackle this one, 111?
Yeah, I actually did not tackle it, but when you watch the videos, you kind of see them do this several times with several examples, and you do get that sort of that idea that that the recursive way of doing it is essentially just taking the mathematical equation and sort of plugging it into the recursive sections. And as far as the iteration goes, since most of the languages that I write in are all procedural, the iteration I think is very natural to me to keep that you keep certain pieces. You keep essentially the state that you are working with, knowledge of it, and then you kind of like add 1 or minus 1 or count whatever it is you're doing on every rotation. You keep changing the state. So I find that doing. In fact, I had the opposite problem, which was I have an easier time with the iteration because I'm so used to doing stuff like that, and then sort of wrapping my head around how to do it with the recursive was more like, oh, you can just add, you could just plug in the equation there, and as long as you catch the base case, everything's fine. That's pretty cool. Yeah.
Okay, that's cool. Actually, we had at least one other person at the KOP group who mentioned that they found the iterative version easier to sort of conceive of as well. And I've also seen the comment made about SICP in general, that in a way it may be easier if you haven't been poisoned by imperative languages first. Because it sort of gives you these preconceptions about what a computer language should be. And I think that's one of the reasons that they're so careful to avoid assignment until after it's established, well, there's all these things that you can do, and without it. And actually, there's some interesting examples in the next section of the book, 1.3, as well, where you can see that you can actually do a lot of computations without access to the kind of tools that you come to expect, where whether it's things as basic as a equals a plus 1. I mean, the response is well, you just said a was a, and now you're saying it's a plus 1. What are you, a liar? So, but the iterative case, I'm not sure it's worth talking through it here. But you can see the interesting thing here is I did run some statistics on it. So I wrote just a little wrapper function to go through the recursive versions and the iterative versions, and then look at the resulting runtimes. So actually, now I think this is a really valuable thing. So if you haven't had a computer science course before, if you haven't sort of thought in terms of algorithmic analysis, the thing that likely was one of the hardest parts of this chapter was the theta analysis. So these comments that this function is theta of n or theta of n squared, or most horrifyingly theta of log of n. So any reactions to that? Have people previously tackled big O notation or theta notation? Does this seem natural to people?
Yeah, I have a computer science degree, and I've had exposure to learning that, and then just determining the running time for different algorithms and such sorts and whatnot.
Okay, cool. Anybody else previously seen Big O or Theta?
I've read a book about algorithm in Python, and then I also read Sedgwick algorithms in C, which is the old version. Now it's algorithms in Java, but I wanted to read it in C, not in Java.
Yeah.
Speaking of Sedgwick, he lectured a Coursera course on algorithms. I think there's like algorithms part 1 and part 2. Those are pretty interesting, so I suggest checking those out.
He actually came to Drexel a while back and gave a talk that I was able to see, and he was quite interesting. And one of the points he made at that talk that I thought was very cool was how important it was to not just theorize about the running time of your programs, but to actually measure the running time of your programs. So, sort of get that empirical piece into the equation. I mean, the useful thing about Big O notation in general, and the authors, I sent a note to the list on this about the difference between Big O notation and Theta notation and these other variants, which are the little o, big omicron, and little omicron. So all of these are ways of sweeping details under the rug, and they're, sort of the reason that both mathematicians and engineers, look very askance whenever computer scientists make a claim. Because in a way, the types of things we're sweeping under the rug aren't the kind of physics things where we say, okay, we're going to assume this body is just a point in space, so we don't have to reason about, all the different, all the effects of a rotating mass might have on its gravitation. Instead, what Big O notation does is it looks at, well, what happens as whatever this process is working on becomes very big. And so you sweep all what they call constant factors under the rug. So if you need to do something to, say, every element in a list, you sort of don't care how long it takes to do each particular thing. Because what's important is you're going to have to look at every element of the list and touch it once in order to get your result. So that would be a linear. Now let's say that, and so sort of here's where it starts to become useful, is when you get into orders that are higher than that, things like n squared. So that is, for every element in a list, you have to touch every other element in the list. And so that means if there's one thing in the list, that's easy, it's 1. If there's 2 things in the list, well, that's 4. If there's 3, it's 9. And so you get this massive explosion in the number of operations. And at that point, how long it takes to do any one thing in that list is sort of less of a concern. Because if you start throwing enough data at this, no matter how big it is, it's just going to completely overwhelm whatever computational resources you can throw at it. And that becomes even worse when you get above n squared, up to things like, n cubed, or, you start getting into exponential, or factorial. You get into these, what they call computationally intractable processes. And so having the knowledge to say, okay, well, this way of solving this problem is something that, if this problem is of a useful size, we will never be able to do it efficiently. You can stop, sort of beating your head against it and come up with a different strategy. And so for a lot of these computationally intractable problems, there are these alternate paths you can take to solving them that maybe give you sort of an approximate guarantee on it's going to be not necessarily the perfect solution, but it's going to be, within a certain percentage of the best solution. And if you wanted the perfect solution, it might take you a million years, but we can get a good enough solution, in a half hour. And so things like that is when sort of beginning to build up these intuitive feels for the shape of the process becomes important. So, I mean, in my estimation, having sort of like a perfect command of all the mathematical notation really is not the key to this chapter. It's really more having the intuition to say, okay, if we have to do this many operations based on this many inputs, this is going to be the shapes of the processes that result. And so we've got some ones coming up as well that are shaped like trees, and trees have different branching factors and stuff like that. So things like that are when it starts to get a little harder to reason about. But the other really significant running time is logarithmic running time. And what that is, I mean, logarithms they sound pretty scary if you haven't thought about them in a while. But really, all a logarithm is the number of times that you can repeatedly divide one number by another number. And that's useful because, potentially very large numbers, you start, so log base 2 is one that we work a lot with as mathematicians. So how many times can you divide something into 2 subproblems? Well, for 1, so if the value is 2 that we're working with, let's say the input is of size 2, well, we can just divide it with it once. But if we can go up to size 4, then it's twice. 8, 3 times. 16, 4 times. So that means, as the size of our input doubles, we only have to do one additional operation. And so if we can come up with a logarithmic process, that means that we can easily scale up our solution in a much better way than if we actually had to touch every element. So again, this is kind of hard to, I mean, if this chapter were your first introduction to this kind of analysis, my opinion is it would be really rough going. And the important thing is really just to sort of remember this idea of the shapes of processes that result, from things like exercise 1.9. Okay, so let's look ahead, or look at a couple of the other ones. Okay, so what did people think of exercise 1.10 before we move on? Anybody manage to get a solution to what H was? Okay, if anybody's talking, I can't hear you. You're all muted. But okay,
I actually got the answer to that, but I kind of cheated because what I did was that I just started plugging in the numbers, and then I was just like, oh, okay. The first 2 were really easy, right? The first 2.
Yeah, exactly.
And that last one, you plug in the number, and it's like it looks like it's behaving, and then you hit 4, and it gives you this really weird number. And then you hit 5. At least on my computer, it wasn't able to do it. It ran out like. But then I noticed, then I just started playing around, and so I was like, oh, I'm essentially sort of doing 2 squared, and squaring that, and or then I forget what it was, but yeah, I kind of cheated, but. Just by plugging in stuff.
Well, plugging it in really is the only way to do it, I think. But I got to say that one gave me fits until I realized that it didn't have a nice, tidy algebraic notation for it.
Right.
So it really is. It turns out that this solution, or this that equation, results in what's called a power tower, for which the formal notation is tetration. And I wasn't going to peek at the answer to this one. I just kept hacking at it until I found something that fit. But really, so what it is it's number of times you raise something to a particular power. So the first one is 2. The second one is 2 squared. The second one is 2 squared squared. The third one is 2 squared squared squared. And at that point, you're talking serious money. So. But that shows, sort of how many, I mean, if you were to try to expand that, each of those processes would be expanding into that many additional sub-operations. And in some cases, you can make your recursions more efficient just by avoiding them. So, for example, I'm not sure if this is discussed in the book. I expect it is. But you can save, for example, a lot of times you can trade time for space. So, for example, for the Fibonacci sequence, which has a lot of recurrences, well, it turns out that you don't actually have to generate all the branches of a tree. If, at each moment, if you just calculate, if you just remember each value as you calculated it, and then okay, well, f of 47, well, we've already calculated f of 47. We can just look it up in this table. So, instead of resulting in this process which, explodes, instead you have a process which is linear in time and linear in space because you're saving an entry for each of these values. So, those are the kind of places where having a feel for what the underlying process looks like can be extremely helpful. Okay, what else do we have here? Okay, so flipping ahead to future. So 112, which was Pascal's triangle. So that was basic. So 112 is basically a procedure that has you, try to come up with a recursive process yourself. Pretty straightforward stuff. That's one, I definitely would recommend trying to tackle if you don't have a strong familiarity with this, because it's pretty straightforward and it gives you, a fairly satisfying result once you get it without too much sinking your time into it. And any comments on 112 from anyone before we go on? Okay, so that's in distinct contrast to exercise 113. Exercise 113 is an extremely brutal proof of a Fibonacci equivalence. If you aren't up on your math, this is probably not going to be the most enjoyable way to spend your SICP hours. It's interesting, and I think sort of the reason they tossed this in here is because it's probably something that that MIT students would be seeing in other courses. They definitely would be, need to be familiar with this type of proof, and so this is a way to sort of work with something familiar. So if you aren't already familiar with it, or if you don't have enough fluency, this is not going to be giving you a lot of additional insights into sort of the practice of programming. And this first chapter in particular, all of these exercises are extremely mathematical. And the reason for this, in my opinion, is that the only tool they've given us to play with is numbers. So if you only have numbers, you're going to have to do math with them because you can't do anything, sort of deeper or more or shaped differently than just a single number. Now, that isn't strictly true because they've actually given us two things to play with. One of them is numbers, and the other one is procedures. So, and that's going to be really significant in the next section. So we're really given two data types to play with. One are the numbers, and the other are things that do things to numbers. And so that, if you haven't played with functional programming before, I think this is sort of one of the key moments where you have a chance to make a jump in your insight into what programming is or can be. And if you've already tackled this in the context of another programming language, if you've been doing Lisp, or if you've been seeing this in JavaScript, this stuff might not be quite as mind-blowing as it has the potential to be. But sort of this is your first dipping your toes into why this stuff is so cool. So at least that's my opinion. So I actually finished. So I transcribed my proof for 113 finally into LaTeX. You probably don't necessarily want to spend your time there if you aren't really in the mood. But if you're interested, it also is kind of interesting because the Fibonacci sequence isn't something that I'd spent a lot of time with previously, and so it gave me some interesting insights. I mean, I've done a lot with other self-organizing processes, and there's a lot of natural processes where the Fibonacci sequence is often used to model them. So that's cool. Okay, so any comments before we move on to section 1, 2, 3? Okay, cool. Alrighty, so exercise 1, 2, 3. Okay, actually there's one here that I only managed to do part of, and that is exercise 114. Okay, so this is another one of these where we're going to look at the shape of a process. And so this has you draw a process by hand. So I whopped together a little thing that kicks out more or less, every time it calls a procedure, it kicks out a node that can be rendered using GraphViz, which is just it's a command line graphing program. that generates pretty graphs. I think if you're looking at either the PDF or the GitHub rendering of the org mode page, it's plugged the picture in there. Actually, the key insight I got out of this problem was exactly how cool org Babel is. Because in order to get that picture in there, I ended up chaining the output of several scheme blocks together. And so that gets pasted as the output into the document. That output is in GraphViz form. So that forms the input to another block, which then pushes it through GraphViz, and then the resulting picture gets embedded in the resulting org file as a link, which when you export it to either HTML or to PDF, that gets automatically embedded. So up until that point, I sort of had been fighting through, what the real value of org mode was, or org Babel was. I was convinced in org mode, but this is the one that really said, okay, this is some darn cool stuff. So the org Babel docs make the comment that this can be used as sort of a meta-programming language, where you basically can do anything in whichever language is most appropriate, and then they're glued together through the medium of text. So in a way, it's sort of like Unix on steroids. So in Unix, you're piping the output of one process to another, and that output is textual. Well, it's the same kind of thing in org Babel, except the things are being passed through labeled blocks in your document, and you can call them with different parameters and things like that. So Tim asked me to give a presentation on org Babel at some point, so I will probably be doing that at a meeting next month if people are interested. I know that Hunter's using org Babel as well, and I think he might be talking about it at the Hack Night, which is coming up on Wednesday. So, yeah. So again, but back to the procedure itself. It's pretty straightforward. Exercise 115. That's the approximation of sign exercise. This isn't really super hard stuff. If you this is just building up your intuition for, okay, if I write this code, what happens? And so you've got the substitutions, you've got and then you've got the analysis. So this is one of the first ones where you start to look at logarithmic processes and why they're so useful. Because it turns out that this is in fact a logarithmic process. So in this case, each recursive call reduces it by a factor of 3 instead of a factor of 2. And one of the interesting things, in my opinion, about logarithms from an algorithmic analysis perspective is that the constant factor, or that the base, doesn't matter. So whether it's log base 2 or log base 1,000, in the long term, it doesn't really matter because that log is just a constant factor. Because you can turn any log into any other log just by more or less multiplying it by a particular constant. So that's kind of a cool insight, but again, it's not something that you really need to have a super sharp grasp of to be going on with. The key is really just to sort of look at how, by subdividing the process in particular ways, you can greatly reduce the computational complexity of the problem you're solving, or at least of the solution to the problem you're solving, because you can have different complexity of solutions depending on how you implement them. And actually, that's one of the things, looking at sorting algorithms, there's a lot of discussion of the computational complexity of sorting algorithms. So you've got, basically your sorting algorithms are either going to be n squared or n log n, or in maybe really good cases they might be on, or on the order of linear. And so that's looking at sort of the way different sorting operations behave. There's a lot of really cool visualizations for this online. That can give you an idea for starting to get a handle on this type of complexity if you haven't done it before. Okay. So the bit on 114 that I didn't do is I didn't actually do the analysis on what the resulting computational complexity was. I just didn't sit down to do the analysis on that. And did anybody else solve that for 114? I'm guessing not. It looks like most people sort of stopped early. Yeah. Again, it's not super key. Okay, so that's 1, 2, 3. Okay. Let's see. 1, 2, 4. Okay, we get exercise 116, iterative exponentiation and logarithmic time. Okay, so this is an example of, sometimes in order to turn your recursive process into your expensive process into a less expensive process, you have to come up with some sort of additional insight into it. And so in this case, the additional insight is based on a particular algebraic identity. And what that algebraic identity does is it lets you change the shape of your recursive calls. So again, instead of keeping the exponentiation operation pending, that your final multiplications, you get to just do a calculation in a particular step and then pass it along to the next call with the next information, or with all the information needed to continue the calculation. And so once again, in the tail call optimization sense of things, you can chuck away that last stack frame, since you don't have to refer to it again, overwrite it, and just keep on running in constant space and linear time. Though in this case, logarithmic time, which is even better. So, because in this case, the number of times you have to perform the operation is logarithmic based on that exponent. Okay, and let's see here. And I did do some some fast measurement of some different values there, and you can see that in terms of the timings on those, more or less, up to input of exponent up to the 20th, you're still not seeing any significant performance hit. So, but it's giving and more or less the numbers on the left there to the left of the timings just show you that it is in fact producing the same result as the other process produces. Okay, exercise 117 and 118 once again are revisiting this question of recursive processes and iterative processes. And the first one, exercise 117, that's really pretty straightforward. A lot of times you just need to translate, exactly what they say in the exercise and turn it into the code that they want you to produce. And the same thing for the iteration in exercise 118. It's just that the key insight is figuring out, what you're subtracting from and what you're adding to, and then passing it along to the next step. So then you've also got the same sort of, that conditional there, where you've got three options. You've got your base case. If it's even, you get to do the super clever speed up step, which gives you your improvement in running time. Otherwise, you're just going to decrement it by 1. You decrement the b by 1, add it to the to your accumulator as it goes along, and then that's more or less ends up being a constant factor based on the number of logarithmic steps you have to have, because you're never going to have more than one additional of that last step than you are of the dividing by 2s, because you're always, if you subtract 1, you're always going to get an even number. Okay, I'm not sure if that explanation was at all clear. What do people think about this one? Anything?
I haven't done it either, so I can't really tell you.
Okay, yeah, that explanation is kind of poleaxing, I'm afraid. But so what else do we have? Exercise 119. Okay, if you're looking for places to allocate your effort, do not allocate your effort to exercise 119. Exercise 119 requires a lot of algebraic manipulation. A lot of algebraic manipulation. And you can do it if you enjoy that kind of math, and it's not that bad. But if you're not comfortable with the math, once again, this isn't going to give you a lot of insight into programming. And if it is one you're skipping, I'd say the thing to take away is that somebody else, if you've got a hard problem, somebody else may already have done something clever that will let you solve this problem a lot faster. So both understanding exactly the problem you're solving and knowing enough to sort of, look at how other people have approached solving this problem can be a good way when you've identified sort of a spot in your program that's a hot spot in terms of the number of operations it's performing. That can be the time when spending a little bit of thought effort can really give you a big performance boost. Okay, so 125. Actually, exercise 120 is one of the two exercises that I did not actually completely complete. Actually, I didn't complete that one at all. So I don't necessarily have much to say about 120 because I really just didn't have a chance to sit it down because I was transcribing proofs. How do people feel about applicative order versus normal order? That was something from section 1.1 that I think a lot of people came away from the discussion at King of Prussia, at least, feeling a bit uncomfortable with. Is there anybody who's still feeling sort of uncertain about applicative order versus normal order? Michael? Okay, so I guess applicative order versus normal order. It's really, so if you look at the way they're specified in section 1.1, normal order basically means before you do any operation, you're going to basically expand everything. So you're going to fully expand all of your trees. And if you go through, there's a couple of exercises. And I think that the exercises they ended up selecting were not ideal ones for really making this clear. Because they sort of attack the question of what happens when these are degenerate cases. Let me see here. I'm just looking to see. I did do an analysis of this. No, it must have been 1.1. So an exercise 1.1 here. Okay. Sorry, one second here. I'm just checking my other screen here to see if I can find this. Okay, so exercise 1.5. I did an analysis that wasn't actually part of the exercise in my write-up there. So if you look at my GitHub, this might help this a little bit. So what you have there is you've got two different trees for a non-perverse a procedure. So if you look at the difference between what happens when you expand the square procedure, so if you expand, three nested squares like there is in the call, in that example, you end up with a large number of operations that have to be performed in order to get a particular result. So if you have 3 nested calls to square, you end up having 8 addition and 7 multiplication steps. So you end up having to perform an exponential number of operations, or because for 3 you have to do 2 to the, if there's 3 nested squares, that means you have to do 2 to the 3rd addition operations and 2 to the 3rd minus 1 multiplication operation. And if there's 4, it's going to be 2 to the 4th and 2 to the 4th minus 1 in order to put them all together. Whereas if you compare that to applicative order, all applicative order means is first you resolve all of your arguments, and then you figure out what the procedure is going to do. And the advantage to that is for something like the square procedure, because for square you're multiplying two arguments together. If you expand those arguments first, then you never have to do that again, because each of the procedures, as you expand along, already have that value available to them. Okay, so is that explanation at all helpful?
Yes.
Okay, cool. So you look at my write-up for section 1.5, and like kind of, even if you just copy out that expansion by hand, that might sort of bootstrap you to the point where you see what they're saying. Applicative order versus normal order isn't something that they make a big deal of throughout the book. They sort of make this the point that this is a way of thinking about what the computer is doing as opposed to what the computer is actually doing. Because in either case, it's not actually rewriting the steps. I mean, as David was asking earlier there about the is there any way to do this sort of thing automatically? Expanding, running through these expansions. So if you were to do something with macro expansion, you try to macro expand one of these things that perversely refers to itself, you can get infinite macro expansion that completely blows out and so on. Any questions on that? I know when somebody's talked a lot. Go ahead.
No question. I think for me too, what helped with that section was going back and rereading about the special forms for conditionals, between the conditional statement and then if statements, and understanding that the predicate gets evaluated first before you go onwards. Just when it was, I think it's exercise 1.6.
I think that's right. Yeah.
Yeah, it helped out quite a bit. Just going back and rereading the previous section, just where it was talking about conditionals and introducing if statements. So.
Yeah, that's interesting because that one is sort of the case where there's something a little different going on, because in either case you don't necessarily. So there's two things. So they did two different examples like that. In one, you assume that you have normal, where in the case of either normal or applicative order evaluation, you don't go down the branch that doesn't get evaluated. But I think exercise 1.6 is the one where you're wrapping the special form in a procedure.
Yeah,
and
definitely.
The key there is that when you wrap that in a procedure, you lose the specialness of the special form. And this is when you, macros become useful, because what they let you do is, if you were using if the putative person in that exercise had actually used a macro instead of a function, it would actually rewrite their code to use if instead of cond, or cond instead of if, whichever it was, and then it would in fact work. Okay, cool. Hey, Hunter finally made it in. Hey, Hunter. Hunter's muted.
Hello.
Okay. Hey. Okay, so it turns out that I'm using a different webcam this time, and if I share my screen, it turns out that it turns off the microphone in the webcam, which is incredibly annoying. So if you're showing your screen, that's great. Hunter, so we're actually just about making it through most of the discussion. I think we're through. Let's see, where did we just make it up to? We just made it up through section 1.2.5. So how far did you make it on the exercises for section 1.2?
I haven't done any of it.
Okay.
I just started a new job, so.
Ah, exciting. Okay, yeah, but definitely priorities. Okay, that's cool. Okay, exercise 1.2.6 then. So exercise section 1.2.6 is sort of an extended example, and I actually really liked section 1.2.6 a lot, because you've got a lot of different sort of takes on the same problem. And so as you work through them, they build on each other as opposed to just being standalone things. So, when you're sort of prioritizing which exercises you're going to work on, I think the exercises from 1 to 6, if you've grasped the basic stuff, are definitely going to give you a good reward in terms of the insight. So, exercise 121 is pretty straightforward. That's just that's more or less just getting you going using the code from the text. And then the next one, which is 122, this is another take on sort of this empirical examination of what your program is doing. So it's actually, okay, we're going to take a procedure, we're going to throw different sizes of input at it and see how it behaves. So, you can actually start to reason about its performance based on observation as opposed to just theoretical analysis. So you can do the theoretical analysis, but you can also say, okay, well, this is theoretically a very good algorithm, and but the constant factors end up completely overwhelming it at the sizes of my problem, so this is a bad option. So this is the case, for example, with, I think, one of the big sorting algorithms. I think quicksort. Quicksort is, if I'm recalling correctly, tends to be really good large sizes, but it tends to be bad at small sizes. So there are some options for sorts where you actually do an adaptive sort based on the size of your input. For small sizes, you'll use one. For large sizes, you'll use another. But actually, one of the most interesting ones is my results for section 128. So if you look at the very, very end of my what I posted there, very last exercise, I've got the measured running times for. Oh, wait a second here. Let me see. Where is it? Well, 1 second here. Sorry. Sorry, I'm just flipping through here. I know I wrote this up actually earlier today. No, actually, exercise 124, putting the format method to work. So my results for that one there, I found very interesting. So if you look at the results of the prime scan that I did there, which is just a little wrapper procedure to hunt through and keep running prime tests until it finds a certain number of primes, and after it's done that, to multiply by 10 and keep scanning. So it's a way to just quickly see how it's performing at different scales. What you see is my results had 2 extremely notable discontinuities in the performance. So from 10 to the 3rd up to 10 to the 9th, you can see the performance is just blindingly fast, 29 milliseconds or whatever it is there at 10 to the 9th. But when it jumps up to 10 to the 10th, you get this almost factor of 10 increase in the running time. And the key there is that that's the range where it no longer fits into a long integer, and so it's transparently promoting it into its internal big integer representation, which can't overflow, which is more expensive. But even more interesting is that jump between 10 to the 19th and 10 to the 20th, and at that it's jumping from 458 milliseconds up to a full 12,000 milliseconds, so like a 26-fold increase. So there's clearly another internal change that's really significant, and I'm not sure what that one is there. I mean, maybe it's even something about the cache overflow. I don't know. But those are the kind of things where actually looking at the performance of your code can show you that the realities when you're running on physical hardware don't always fit your predictions. Now, of course, depending if you had an ON procedure instead of a log N procedure, you would have completely blown out your running time long before those giant sizes became anything close to an issue, because you could just never hope of even beginning to solve them. So, any thoughts on that one there? Comments?
When I was trying out some of these, like measuring how much my functions take, for a lot of them, I kept running into issues where the iterative and the other one, the recursive, were doing the same exact thing. So I'm not quite sure what I was doing wrong in terms of timing. I mean, I could blow it out. Like, I could always blow out the recursive because I would run into the stack issue. But into timing stuff, almost never. They almost were the same. The earlier ones, because I only worked on the earlier ones, and I was timing them just to see if there were differences, but I couldn't tell any difference in the timing.
Well, actually, and that's an interesting distinction there. It's the difference between time and space, because you have to think about sort of both the time complexity and the space complexity of your program. So, for example, those recursive procedures you were looking at were, in fact, linear in terms of the time, because they just perform one operation for each. But the key there is they were also linear in terms of space, because for every recursive call, you had to save a recursive call. You had to save that stack frame that was associated with it, so you could go back and continue performing the operation at a later time. So that's why your stack's blowing out. And that's actually a point that the authors, sort of talk around a little bit, but they don't really get deep into the, those distinctions between time and space, at least that I recall. This is kind of a quick and dirty introduction to a lot of this stuff. So, yeah. And sometimes, you have to get fairly large before you start to see any sort of difference at all. I can't remember which problem it was. It might even have been that one. There's ranges where things that were very expensive and slow to compute at the times when the book was written. Now these problem sizes are just so small as to be barely noticeable in terms of the running time they take. And so actually that's one, you see that actually, if Hunter has it up on his screen share at the moment there's a require line, which he just commented out because he's not using Racket. But in order to pull in a random number generator that would actually generate random numbers larger than the size of max long, or whatever the equivalent is in terms of the Racket internal representation.
Yeah, sorry, I don't have Racket.
So, actually, for me, so that. Oh no, that's yeah. Actually, so I did find that Racket is just awesome in terms of its ability to deal with packages. So you just stick a reference in to a planet is the Racket repository, and it'll just automatically pull it down transparently in the background, including, and I sent this to the Clojadelphia list, there's a directive you can stick in. Neil Van Dyke put together a compatibility library so that Racket language will look like the language that's used in SICP, because there's a few places where the dialective scheme that's used in the book is different than Racket. And that will be particularly significant come section 2.2 or 2.3, I forget what it is, because that is focused on a picture language, they call it. And there is a library that's pulled in by that directive, which will allow you to do all the picture language stuff. And I don't know that, I guess it's out there for MIT Scheme, but I don't know how easy it is to install or anything like that.
There's also,
so
if you're following the Berkeley stuff, there's UCB Scheme, which you can get, which goes along with the Berkeley course, and I think it's closer to what they do in the SICP textbook.
Okay, that's cool. One of the main reasons I ended up selecting Racket myself was because it worked really nicely with org Babel and Geyser specifically. So Geyser's got support for, I think, Guile and Racket. So I didn't have strong preferences either way, so I just went with Racket since it had these compatibility libraries, and it let me keep working in Emacs without pain. So you're using Chicken, you said, right, Hunter?
Yeah, but I'm really curious. I've been looking and looking for somebody who has a good reference for using multiple schemes, like setting up and easily switching between multiple schemes. And I haven't found any reference on a good implementation for that. Because I want to be able to run MIT, Chicken, and Racket simultaneously and switch between them. So.
Yeah, I definitely would be interested to if you manage to find anything out about that.
Yeah, I've been looking. I'll probably have to write my own thing. So.
Yeah. Okay, cool. So I don't know that we need to go through all of the exercises for 1, 2, 6. I mean, they all sort of build on each other. They're all sort of in the same space. The value in these, I'd say, is more in the doing than in the reading. So if you make it through them, if you actually can spend a little bit of time working through them, you're like half of a weekend day or something like that, you can probably make some progress on those. I did note that a couple of these would have been a lot easier if they introduced things like lists of numbers and so on, and streams, and stuff we'll be getting to later. So you're working with pretty rudimentary tools, but part of the challenge is working with those rudimentary tools and seeing what you can produce out of them. I guess one last thing that I will mention specifically is at the end of section 1.1, they introduced what they call block structure, which is the black box where you've got a procedure nested inside of another procedure. Yeah. And we discussed that a little bit earlier. But one of the interesting keys there is that each of those internal procedures can access the the named variables in the outer scope. So it can see. So for example, on page 30 of the book, right at the end of section 1.1, there is an example where they rewrite the square root procedure with good enough nested in. And what that means is you don't have to pass x as a value to that lower level procedure because it can see it, because it's running in that context. And sort of going back and taking a look at that and looking at, for example, when you're doing some of these exercises, how you can structure your procedures similarly, that's going to pay off in the next section, section 1.3, because you're going to be doing similar sorts of things a lot. Because once you get to the point where you're using higher order procedures, or higher order functions, as we'd normally say, since they're being very careful to avoid the word function, so you aren't conflating it with the mathematical term function. Once you start passing those functions around, the key is once you've instantiated that procedure still has the value of whatever that variable is that it had when it was instantiated. So that means, if you pass that good enough guess out somewhere else, it remembers what that x is. And so that's what's called, usually in functional programming, a closure. And the authors speak very harshly of the term closure. I forget if that's in the book itself or in the teacher's guide, because it has a different meaning in the context of mathematics, which is to say that the function is closed over a particular range. That means that if a function is, if you operate on a value in a range, the result will also be in that range, which is completely different than this other sense of closure, where the inner procedure closes over the values that are in its scope, and it will access them, which means that if you're executing it somewhere else that has procedures with or variables with the same name, they aren't going to interfere. And so that's very important from sort of making sure that each of your procedures remains a black box. That it remains, you've probably heard the term referentially transparent, which means that if you call it more than once, you're always going to get the same value, no matter what the greater context is where you are executing that procedure. So I guess that's the last main point I wanted to make about this. And we can certainly discuss any other aspects of this for as long as anybody would like.
Well, I'm good. I actually I don't have much more to say.
Okay.
But thank you so much.
Oh yeah, sure.
Thanks for the talk.
Yeah.
Okay.
Paul, this has been invaluable for me.
Oh great. Well, I'm glad to hear that. Thank you.
Thank you for putting the code samples up on GitHub. It looks really nice.
Yeah, super helpful.
Oh,
Yeah, and
Yeah, that was
halfway in, I started looking into how to get org mode to work in Vim. So, so I kind of got a little bit distracted, but I was listening very carefully. Well,
okay.
As careful as I can.
Yeah. Yeah, I mean, so if you haven't tackled the exercises, my advice is, don't get too bogged down. So if you can't make it through all the exercises, don't let it sort of discourage you from keeping going with the book. I mean, so maybe you don't manage to get, every last ounce of insight out of it. Doesn't matter, because, you can always go back and look at this in the future and you'll have seen it once. I mean, I first tackled SICP 5-6 years ago, and I made it to section 3.1 or something like that before I bogged down. So, it's really interesting going back to look at these early sections based on all sort of the experience I've had with functional programming in the meanwhile. And, a lot of this now seems really clear. So it's not sort of the blinding insight that it might have been if I'd really been able to grok it the first time through. So you sort of get just keep hacking at it. Spend some time on the exercises as you can. I will say though that if you can spend some time doing the exercises, that's definitely a valuable thing to do. So, whichever ones. I did post some suggestions as to which exercises, maybe rat holes that will end up, sinking a lot of time if you're trying to do everything.
Do you feel like a background in mathematics would enable more clarity, I guess, in going through just kind of understanding, talking about shape of processes and whatnot, or procedures and whatnot?
So I think that previous computer science training, it forces you to go through a lot of that. I think that, in fact, okay, so from my opinion, the mathematics, not the algorithmic analysis stuff, but sort of the mathematics that are a subject to a lot of these functions, stuff like the Fibonacci numbers and testing for primality, that's actually a distraction in terms of figuring that out. Those are examples. And in the next section, there's going to be a lot of, it's either two something or three something. There's going to be a lot of examples from electronics, which is an area I personally have very little familiarity with. But again, for MIT undergrads, this would have been something, they would have been simultaneously taking a course in this stuff. So this is, so you're using it as an easy way to start thinking about this stuff, using terms you're already familiar with. And the problem is, for us as, programmers who don't necessarily have, we aren't MIT undergrads necessarily, we haven't had the same training, we aren't going through the same things, we aren't, there's no, it can be a little difficult to figure out, sort of what's the key to what's going on. So all this stuff with primes, the key is, what happens to the procedures, not the fact that you're working with prime numbers. let's see, there was something else I wanted to say about that.
Well, real quick, Paul, that's a really good point.
Yeah.
And I really like the way you just phrased that. And the algorithmic aspect is the really important thing in this stuff, and not the math. And I'm always amazed. I'm from a background of Perl, and thinking about programming in more of a linguistic context. And it's amazing to me how sometimes how unmathematical Lisp seems and functional programming can seem, given the fact that it is one of the closest expressions to lambda calculus that we have in modern programming. And it's very strange how, you know, algorithm focus is not necessarily math or calculus, and in the classical, like, classroom university sense. So I really like the way you just phrased that a lot.
Yeah, and I think that as we move into stuff like section or chapter 2, that's going to become a little clearer, because there's going to be some more mathematics in section 2.1, but we'll be able to finally start working with things that are not just straight raw mathematical functions that call themselves recursively. And as we get even farther into the book, okay, so it's chapter 3, which has the digital circuit simulator. But once we start getting into building the language itself, so starting to implement scheme in scheme, they're working on things like the scoping, that's when I think the real value of this, sticking with the book through these early stages, which can be a little rough, will start to pay off.
Do you think, I mean, if anybody has like a good resource for, I guess, like algorithmic analysis, or at least an introduction, I guess, for others here, like you were talking about, theta versus like big O, like, do you think like someone could maybe just post a link somewhere, just if they found a good resource?
If you want to, go ahead, David.
Oh, I was just going to point out that you sent out you posted a post on in the meetup page, and I found that pretty useful. I'm not sure if anyone else saw it, but it was essentially a definition of all that stuff. I read through that, and I thought that was pretty useful.
Yeah, I read up a fast, high-level analysis. I mean, there's a bunch of web pages out there. If you want a fairly straightforward book on it, the Robert Sedgwick Algorithms book is a good one. Okay. One of the standard texts on algorithms is, what is it, Introduction to Algorithms. It's CRLS. I'm trying to remember exactly what the title of the book is. Introduction to Algorithms, I think.
Is that like the Nuth book?
Yeah, it's Introduction to Algorithms. It's an MIT Press book. It's by Corman. Waiting for the page to refresh here. Sorry, 1 second here. That's what I used for my first graduate level algorithms course. It could be used for an undergraduate level course as well. Corman Rives. Nah. Okay, this is taking forever to refresh here. Okay, we'll try the Amazon page. Yeah, Thomas Corman is the main author, C-O-R-M-E-N. It's called Introduction to Algorithms. It's actually extremely comprehensive, so it's not necessarily the easiest. It's more of an ongoing reference. It's I'd say it might be a little rough to tackle without any previous algorithms experience. Okay, so it's Corman, Leiserson, Rivest, and Stein. but Introduction to Algorithms, 3rd edition is the one I have from MIT Press. I haven't worked through all of the Sedgwick book, the Sedgwick Algorithms book, though I have looked at it. I own a copy. It looks pretty good. Yeah, but a lot of it really is just sort of starting to, force yourself to do all these analyses, because a lot of it does not come easily. And there are some things that are, so I mean, a lot of this stuff is based off of solving what are called recurrence relations. So you more or less figure out, okay, so if this calls this, okay, we're going to end up calling it this many times, and so on. So there's a lot of that. So there is a sort of a mathematical underpinning to it. And then there's also, on the other side of things, you've got the mathematical specifications of these different notations themselves. So I guess I'll just kind of mention one key insight here, and that is that the difference between big O and theta is more or less the difference between worst case. So you're going to say that no matter what, in the case of big O, the algorithm is never going to perform worse than this. Or in the case of theta, you're saying, okay, this is the behavior of this algorithm. And the other side of things is the Omicron notation, which you almost never see outside of formal algorithm courses, but it's part of the specification. And that is, whatever this is it's going to be better than this this performance, or that is to say, no matter what, we have to do at least this many operations to solve this problem. And so you combine the Omicron notation, which says, okay, we have to perform at least this many operations to solve this problem, with the big O notation, which is we will never have to perform more than this many operations to solve this problem for the theta, because then you've provided both an upper bound and a lower bound, so you know exactly what the performance characteristics of the algorithm is. And another reason that it's important to have these different forms is that it's not always possible to get clean bounds for algorithms. So you may have really good best case behavior, but really bad worst case behavior. And so you can have sort of these complicated functions. For the most part, for most software engineering type stuff, a seat of the pants knowledge will take you a long way. And spending some time sort of seeing why popular algorithms behave the way they do will take you, again, a lot of the way towards seeing the value in it. And then a lot of it is looking at, okay, well, here's a description of these data structures. So on the other side of data structures, you have, you often have algorithms and data structures courses. And so the two kind of go together, because data structures are a way of organizing your data so that you can perform certain operations on them efficiently. And so you can say that as a consequence of building this binary tree, for example, if we're trying to find something in this binary tree, we're never going to have to perform more than log n operations, because, by the way we're constructing the tree will always have a height which is log n of the number of nodes, because at each level we're dividing by 2. And so, again, so if you get a book, I'd say that probably the Sedgwick algorithms would be a good place to start with that. And just look at, that you usually, and online for like, if you look, actually, a really good place to look for this stuff is programming interview sites, because they often have lists of this kind of thing, commonly encountered performance properties for data structures and so on. And if you, okay, so you find one of these lists and you say, okay, well, this kind of graph operation takes this amount of time. Well, look at then the algorithm itself, some code for that algorithm, and say, okay, well, let's see why, if this is ON, it means that we have to visit every element of the input once. Or if it's log a 3 of n, why at each step we're dividing the input by 3. So we're never going to have to do that more than a tree of 3 times at each level.
Cool. Thank you.
Oh yeah, sure. Okay. Any other thoughts, comments? Cool. Okay, so Hunter just posted PDF, which might be of interest to some people there. Okay, so next up is section 1.3. Section 1.3 has some moderately fun exercises in it. I enjoyed it. I posted sort of my thoughts on what's coming up for section 1.3 in the book, and there is some cool stuff in there. Coolest thing, in my opinion, something that I had not properly grokked before, is the equivalence between let and lambda. So if you haven't done much Lisp before, that may not mean anything to you. But if you look at, what we've been building up to in section 1.3 is lambdas. If you look at the teaching notes, they say that when you, the professor, are starting to teach a course using SICP, when you're organizing your course, you may want to address section 1.3 before 1.2 to introduce lambdas as early as possible. So just as a preview, all a lambda is a procedure. So when you say define blah as a procedure, you've got your name, and then there's what the name is naming. And the name is this sort of abstract framework for a process that you can instantiate at any point by invoking it. And the key point is that that name is not necessary. You just want to come up with this this abstract process, this abstract concept of a procedure you can pass around, because that's where the real value is going to come in. Because then you can, when you're writing your higher order procedures, you can, for example, say, okay, I have a procedure that does something to one object. Then you can have a higher order procedure that says, I have a list of objects, and I know how to do one thing, and that could be anything, to each object in this list. And then what that lets you do is stitch those two things together, and then all of a sudden you can perform any single operation on everything in a list. And that is where you're starting to really get into what makes Lisp cool. If you write Python, you can do all this kind of thing. Just about every language has started to introduce these kind of higher order procedures if it has the facilities to implement them. So what I just described is map. They don't call it map yet, but in section 2, or excuse me, chapter 2, when we get there, we're going to finally start getting sequences, and we can start taking advantage of all this cool stuff. Chapter 1, it's just laying the groundwork so we can do super cool stuff later on. Sorry, what I was saying about let. Let is effectively a syntactic sugar, as they call it, for a lambda. And that was sort of the one real revelation for me this time through in 1.3. I had to spend a little bit staring at that code before I really understood why a let is just sort of a reversed way to specify the lambda. And if you get that, that actually is a really cool thing.
Is this let the same as the let that you have in Clojure by any chance?
Yep, that's the one.
Cool.
Yeah, so that bit I was talking about earlier, where you have a function closing over over the values in its context. That's basically what's going on with the lambda. It's a way of so basically what you end up with is a lambda, an anonymous procedure that has a couple of slots in it. And then at the end, you call that anonymous procedure with a few values. Well, it turns out that if you rewrite that, you can get your nice, tidy let form, where it says, okay, here's the slot, which is the name, and here's the value we're going to put in the name. You just turn that around, put the call at the end, suddenly you've got a lambda. So hopefully that primes you a little bit for when you hit that point in the chapter. It's a little hard to hit visually. I mean, if somebody had described that to me, I don't think I would have gotten it. The key is really to just stare at that code until it clicks.
So is it the same as
Okay.
lambda in Python, or I don't know if you're familiar with Python or anonymous functions in JavaScript?
It's closer to anonymous functions in JavaScript. The key annoyance with Python lambdas, as I recall, is that they are limited to a single line because they peeve Guido for reasons that are completely unknown.
Yep.
So Guido does not want to make Python an actual functional language. So you can do anonymous functions in Python, but they have to be very, very short. And so that ends up with you doing one thing, so you end up writing the other function as a named procedure, and then calling it in a lambda if it's going to be complicated, if you need to do more than a single thing in the context of that lambda. But yes, after I'd been writing Clojure for a while, it totally changed the way I wrote Python, because it drove me nuts that I couldn't do things the way I was used to, because there's these very tidy ways you can specify things using these higher order functions. You could say, okay, we'll take the list, we're going to do everything to this list. We have this list, we're going to reduce this list by collapsing each item into an accumulator. And so, yeah, that's exactly the same thing. And if you've made the jump in a language like Python or JavaScript already, once again, you're going to be a lot of the way there. So this is going to just sort of click what you know already into a very slightly new context.
Thank you for your answer.
Oh, sure. Okay, anyone else? Any thoughts? Shall we wrap it up for the night here?
Shall we talk about when the next one's going to be, or should we just do that online?
Yeah, that's an interesting question. So, yeah, probably could be worth discussing. There's clearly a lot of interest in this, and how many people have strong... So, okay, one thing I'm noting is that a lot of people here didn't actually have time to make it through 1.2 completely before this call. And that's been a month since the last one, and I think this is probably going to be a pattern as we go on. I think everybody's going to be having problems finding enough time to do this. I've been fortunate that I've had a few extra slots where I can spend some time really digging into this stuff, and which is why we got the write-ups. I don't know that I'll be able to keep doing that. But a lot of people actually at the in-person session at King of Prussia were saying that they were worried about being able to keep up with the book. Now, I don't think we can... Go ahead.
Oh, I was going to say that I was thinking that maybe we can structure it a little bit different, and I was actually going to make a suggestion in the other class that maybe it would be to focus ourselves a little bit more if we chose to like a specific section that was like, okay, this is going to be our section, and we can talk about it. Not like the whole thing, but or maybe the one exercise. And we say, okay, I might not get through all the exercises, but I'm going to do this one exercise, and when it comes to the discussion, well, I'll run that discussion or on that exercise. I was thinking that maybe that's a way that we could at least have more sort of participation.
That would be awesome, because I would love to get more participation out of these.
Yeah.
I think that's a good idea. I like that.
I love it, yeah.
Because I think, 15 exercises is a bit overwhelming. I mean, for, people not...
Right, and I was thinking, well, I mean, like, to have to do all of them to give a talk or to talk about, I think that's a bit overwhelming. But if we could say, well, let's just pick whatever exercises, and we could say, okay, so, David, you do the exercise, 1.31 or 1.3, whatever it is, and Hunter, you do this one, but we have to kind of like pick the ones that we're going to work on, and then we get to talk about what our experience was and whatnot.
Maybe Paul can comment on how problematic it is to do that given the cumulative nature of the problems. Is that an issue?
So I think for section 1.3, not at all.
Okay.
There's a few that build on each other. So like there's a few that form a series, and so it could be useful. I mean, probably it would be most useful if there's ones that form a series for somebody to talk on those. So like for the next section, so like section, what is it, exercise 145, I think, 1.45. I don't know that there's going to be a lot. That one's going to be painful. That's one of the two I haven't solved in that section yet. So I don't. That's the kind of exercise where I don't think there's going to be a lot of super value. Actually, okay, there's one exercise. Let me see if I can find which one it is here. Well, it doesn't matter. But the key is it says that a good answer to this exercise is probably worth a PhD. Somewhere in chapter 3, I think. So some of them are what we could probably call open-ended. So
yeah, let's toss those.
Yeah. So, but yeah, I think that definitely. Well, maybe we can open up a discussion on the mailing list about this, because I think this is something that will benefit all 3 sections, because it's useful, because I know that people typically don't go to more than one. I know Steve's the only one who's probably going to all 3. Actually, Steve's not going to this one. Steve's going to the 2 in-person ones. I usually make it to the King of Prussia one because the other one conflicts with the Philadelphia Linux Users Group. So probably having multiple people. So one person who's going to discuss it at Philly, one person who's going to discuss it at King of Prussia, one person who's going to discuss it online. Even if we don't get maximum coverage, I think that would be great. I mean, one thing I found that in running the Philadelphia Linux Users Group is if you get somebody to give a talk on something, they become highly motivated to learn it.
Right. Yeah.
So if you're signed up to say, okay, well, I'm going to at least talk about these exercises, yeah, I think that's great in terms of getting engagement.
Yeah. Well, I was saying, talking. You don't have to commit to like a lot of exercises, just like one. Like this is the exercise that I will talk about, and then just get really good at that one exercise.
Yeah.
And then at least that way, I think we'll get a little bit more participation in that. I'd like to participate more.
Hey, that's great. Yeah, and actually, the other thing is that it could be useful to have even more than one person to cover them, because as we can see, we had 15 people who RSVP'd for this here, and what's 1, 2, 3, 4, 5, 6, 7, 8. So we've got 9 people who actually are participating. We've got 8 on the call and 1 person viewing the YouTube stream at the moment. So, yeah, so I think that if multiple people want to discuss the same exercise, that's probably good. I posted to the Clojadelphia mailing list earlier my reactions to the exercises. At that point, I had not actually looked that closely at exercise 1.45, so I don't think I commented quite as strongly on it as I would now. But based on that, if you see any exercises in that list that you'd like to jump on, go for it. We might want to figure out a way to sort of do a more formal sign-up. I'm not sure what that way is, to sort of do this. So, because once again, depending on which section you're planning on going to, it could be useful to have multiple people covering it. I'm really not a fan of the per-meeting discussions for meetup.com. I think those are just terrible. It's a terrible interface. It's fragmented, and it's almost impossible to recover the stuff. And I know we discussed briefly on the mailing list, is it useful to have the separate Google group for this group? I mean, my basic reaction is, I think it's useful from a community perspective to keep everybody discussing things on the same mailing list and just have people ignore the stuff they're not interested in. So keep it on the main.
I totally agree with you there, because I was having problems kind of keeping track of what am I, where do I go to look at stuff. So, yeah.
I think I might see if it's possible to turn off per meeting comments in the meetup group. And I'll discuss with Steve that maybe it's not ideal to go with the separate Google group for SICP. I mean, unless people are strongly object to seeing all the messages, personally, I don't think the volume is going to be that high that it's going to be a real problem for people. I mean, you know, I'm on so many mailing lists at this point, you know, any traffic this list could generate would not be significant. And if it is a problem, you can always set it for digest form. Okay, so yeah, I think probably what we should do is take this discussion to the mailing list. David, since it's your idea, do you want to send that to the list? I think that's awesome.
Real quick, I'll make a shared Excel Google Doc.
Oh yeah, that's a perfect idea. That's a great idea. In fact, I mean, if you share the, you know, the Google Doc, and we just put our names and then just list out the exercises for the next section, we can just, you know, X, and then I guess we'll just have to decide like how many, like no more than 2 or no more than 3. I don't know how that's going to work out, but maybe we can figure that out as we sign up.
Yeah, I'd say let's play it by ear. I mean, you know, this is a flexible process. Let's just let's give it a try. I mean, just like we did with these here. I mean, I had no idea what was going to happen when I suggested we do these online ones here. So
okay,
let's just keep.
So Paul, just to be clear, what do you need from me?
Just send. Well, I mean, somebody should. All I'm saying is somebody should send this suggestion. Just write up this idea that people should, you know, sort of take ownership of an exercise that they want to discuss for an upcoming meeting.
All right, fantastic. Yeah, I'll do that.
And also potentially, you know, have a backup person as well, so somebody else could sign up for it if there's one they really like. So if we aren't going to get perfect coverage. So yeah, that would be cool.
Great.
Okay, any final words? If not, we can wrap up the broadcast here. I'm not sure how useful this will be to others. I will try to, we've had a couple requests. I've had at least, Tim sent one to the list, and somebody sent me one privately asking for the video of this to be available publicly. I will see what's required to sort of trim this a little bit at the front and the end. I'm not sure if we can do much trimming of the middle without a lot more effort than I personally am willing to put in.
Right.
Unfortunately, we don't have the really good video for this, so it would be much more useful if we were actually showing the screen during this. So before the next meeting, the online section, I'll try to get that issue sorted out with my microphone. But I think it probably, I mean, if somebody is motivated enough to sit through sort of this, you know, rambling 2-hour-long conversation on SICP, you know, they should be able to. I'll probably cut off this bit at the end here where we're discussing procedural stuff as well, if I can.
Cool. Well, thank you again. Thank you. That was great.
Oh, well, thanks everyone for jumping in here.
Thanks, Paul.
Yeah,
thanks,
Paul.
Thanks, Paul.
Okay, thanks everyone.
Bye.
Talk to you soon.
All right. Thank you.
Thank
Good night.